I think with that we can start. So welcome everyone, and thank you for joining us today for a new BUGSENG webinar. This is Lavinia, your host. I hope you all had a nice summer and a reasonably not too stressful back to work couple of weeks. To kick off this new season, we are joined today by our partners and your friends at Solids Sands. You surely know Solids Sands as a leading provider of compiler and library testing and qualification technology. Their super test suite is known all over. We even use it in BUGSENG, in fact, as part of our tool qualification service. We are here today because BUGSENG and Solids Sands recently joined forces to release a new invaluable tool for compiler qualification. The tool is called Application Hazard Scanner. It's configured for your specific use case, and it allows you to automatically enforce the compiler defects that are defined in the qualification report resulting from Solids Sands compiler qualification service. The application as a scanner is built with a ECLAIR static analysis tool, so it can be configured to perform language subsetting analysis, for instance, for MISRA, and even to be part of your continuous integration platform. Of course, our speakers will tell us all about it in just a second. So please let's welcome Marcel Beemster, CTO of Solids Sands, and Roberto Bagnara, software verification expert and co-founder of BUGSENG.
Hello. So I will start and then I will hand over to Marcel for compiler qualification. Here is a brief outline. I will remind the audience some important fact about the C language, and then I will explain what is language subsetting. Marcel will go through compiler qualification, and then we will see the application as a scanner. So the rhetorical question I often ask is, do you want to reason about your programs in assembly code or in C or C++? And usually the answer is we want to program and reason about programs in C or in C++ because it's much easier. However, things have to be taken into account, and these things have to do with the C language definition. The C language has a lot of advantages, and it is no surprise that after almost 50 years since its introduction is again the most used language in all industry sectors, and particular in embedded systems. The reasons are very strong reasons. So there exist compilers for C for almost any processor. And the compiler code is very efficient and without hidden costs, meaning that a programmer can easily guess in advance the running time of a fragment of C. C allows writing compact code. There are many built-in operators. You can do very complex things without writing too much. It's defined by an ISO standard. And possibly using a little bit of extensions, it allows easy access to the hardware. It has a long history of usage in all sorts of systems, including critical systems, and it is widely supported by tools. So C has a lot of advantages, but it has disadvantages as well. So they come from the fact that the C standardization working group to which I belong has always been faithful to the spirit of the language, which is a spirit that allows the programmer to do everything, because oftentimes the programmer knows what has to be done, and this freedom is necessary to complex several things that are in the scope of application of C. However, this has significant drawbacks. So this fact of not constraining the programmer and letting the programmer do things, anything, is bad for safety and security. Where is the problem? The problem stems from the definition of behavior in the C language. Behavior is something that is externally observable. So it's something that can be observed from the outside. And because of this definition, the compilers resort on this informal rule, that so-called as-if rule, saying that the compiler can do any transformation that preserves the observable behavior. So in other words, for example, if you increment x by 1 in the program, maybe because you wrote plus x, maybe x will actually be incremented by 1 or maybe not. The compiler might discover that the value of the incremented value of x is no longer needed, or it may discover that immediately after it's incremented again, so it will generate an increment by 2 instead of 2 increments by 1. So all this is made possible by the fact that incrementing an internal variable is not observable from the outside. And the as-if rule is not just there in C, it's in many language implementations. Basically, all in language implementations based on compilation technology, optimizing compilation technology as some sort of as-if rule, because in this latitude, we have the vast majority of possibilities for the compiler to generate efficient code. So there are behaviors that are not fully defined in C. And there are different varieties of non-completely defined behavior. Let's start from the most dangerous one, which is called undefined behavior. When we have undefined behavior, no guarantees are provided whatsoever. Anything can happen, okay? No requirement means absolutely no requirements, so the program may crash or may exhibit erratic behavior of any kind. In the very lucky case, the program may fail to compile, okay? This is also allowed. And for people who don't get this complete absence of specification, the saying has been invented that it may format your hard disk. Okay, so this is actually true. So it may happen. So if somewhere in the program memory there is some piece of the operating system that formats the hard disk and you have undefined behavior, there is nothing preventing this piece of code to go into execution. What happens normally is that the compiler assumes undefined behavior does not happen. And if it does happen, it's a fault of the programmer. This is the point of view of the standard. Okay, the programmer has violated the contract, and so the warranty is void. Let us see an example. One of the many undefined behaviors of C is when a program attempts to modify a string literal, so a constant of type string. Here we have a simple program where there is a string literal hello with 3 exclamation marks. And the programmer said, well, 3 is too much. Let me neutralize 2 of them by writing a null terminator into position 6 of this string literal. So, well, it doesn't work. In general, it doesn't work. It may work by chance somewhere, but it's undefined behavior. What can happen is that the string literals are stored into read-only memory, and when you try to write to read-only memory, what may happen is another exception. So the memory management unit can detect the error and trigger another exception that, from the point of view of the language, is completely undefined. We will see another reason later about why this is undefined behavior. Then we have unspecified behavior. This is when there are 2 or more possibilities to do one thing, there are 2 or more possible choices, and the standard doesn't impose any requirements. So let's immediately see an example. Here we have an addition. We see something plus something else. What is evaluated first? Is it evaluated first the plus argument on the left-hand side or the one on the right-hand side? Well, it's unspecified, so anything can happen. So this program can print hello world, which is probably what the programmer wanted, or it can print word hello, which is probably not what programmer wanted. I've been a bit quick in this description, and let me go back. So the standard imposes no further requirements on which is chosen among these possibilities in any instance. What does this mean? It means that I may have several lines of exactly like this one, and the choice made in one line and the choice made in the other line need not be consistent. And similarly, there is no guarantee of consistency if I change the compilation option. So maybe it will print hello world if I enable optimization, and it will print word hello if I disable optimization. Okay, so it's unspecified. Unspecified means that no consistency, no documentation about what happens in each instance. And then there is implementation defined behavior. This is a kind of behavior that everybody knows. Everybody knows that there are implementations of the C language for 16-bit machines and implementation for 32-bit machines. And so the size of an int is implementation defined. So on some implementation, it will be a 16-bit. In other implementation, it will be 32-bit. But there are many, many other implementation defined behaviors, actually more than 100. Okay. So why is C not fully defined? We have seen undefined behavior, unspecified behavior, implementation defined behavior. And there is another variety, which is local specific behavior, that for this presentation is not important. So let me skip it. So why is the standardizer language not fully defined? The point is that this way, implementing compilers is easier. More precisely, it is easier to generate, to produce compilers that generate fast code. Let me expand a little bit on this. So let's go back to the undefined behavior about modifying string literals. So the behavior is undefined when the program attempts to modify string literal. We have seen one reason. String literals may be in read-only memory. Here is another reason. When in a program we have literals like tail and head tail, you see that tail occurs within head tail. Well, the compiler program can store in memory just head tail and use a pointer to the fifth character whenever a representation for tail is needed. And so changing one string may also change the other in a way that is completely hidden to the programmer. But the compiler can assume this will never happen because it's undefined behavior. The programmer is supposed to never, ever try to modify a string literal. And this way, the compiler may generate more efficient code, in this case, space-efficient code, because the representation of string literal may be factorized. Another example is even more instructive. So there is an undefined behavior that goes as follows. It's undefined behavior when an expression is shifted by a negative number or by an amount greater than or equal to the width of the promoted expression. So let's start from the negative thing. So what might mean to shift a quantity -2 positions to the right? We may stipulate, if we are to invent another language, that shifting -2 positions to the right is shifting 2 positions to the left. But if C was defined this way, whenever the compiler is not able to detect the sign of the shift count, it would have to generate code to check the sign. If it is negative, it should compute the absolute value, then it should reverse the direction of shifting. This is not the spirit of the language. So if you want to play with negative shift count, you do it yourself. So if you do so, it's undefined behavior. Now, it's a little bit more subtle to understand why it's a problem to shift a 32-bit quantity by 32 bits position to the left. So, well, many people believe that shifting to the left is the same as pushing zeros to the right. So if I push 32 or more zeros from the right, the result would be 0. I mean, I would kick out all the other bits. No? Well, no. Not on all architectures. For example, in very popular architectures like the Intel ones, both 32 and 64 bits, the first thing that happens to the shift count is that it is masked. So only the 5 low order bits of the shift count are retained. Why is this done? This is done because it is easier to provide an upper bound to the execution time of the shift instruction. So it will have to shift at most by 31 positions, 5 bits. So on these machines, shifting by 32 is the same as shifting by 32 masked. But 32 masked with that mask, so retaining only the 5 low order bits, is 0. So it's the same as shifting by 0 position, which is the same as doing nothing. So the previous interpretation was that the result would be 0. And now we see that on this architecture, the result would be unchanged. I wouldn't change its value. So, well, again, C leaves the behavior undefined for speed and ease of implementation. And this is something very common in C. Whenever there is the possibility of mapping a high-level construct of the language to one machine instruction or to 2 machine instructions, so this is done. And this is done, and since there is a variability between the machine instruction provided by different architectures, this is one of the main reasons behind undefined behavior. So let me now introduce language subsetting. The important point to understand is that the strong point of C, the ones with which I have opened the presentation, are tied tightly to the weaknesses of C. So they have the same origin. For example, we have seen that the fact that it is easy to write efficient compilers for almost any architecture is one of the main reasons behind the non-definite behavior. The fact that we can have efficient code with no hidden costs is because there is no runtime error checking whatsoever. And another reason behind non-definite behavior is due to the fact that there are many compilers, which is a good thing, that there is an ISO standard, which is a good thing, but the two things together mean that if there are compilers that have historically implemented the same thing in 2 different ways, okay, that thing will most likely have to remain non-completely defined, okay? You cannot say to a major or even a minor vendor of compiler, from tomorrow, your compiler cannot legitimately be called a C compiler because we have changed the standard, okay? So the fact that it is easy to access the hardware is because, well, the same reason allows you to easily corrupt the program state if you make a mistake. And the fact that you can write compact code due to the generous provision of built-in operators is also the reason why the language can be easily misunderstood and misused. So what do? Industry decided to resort to language subsetting. So we didn't say, okay, C is too dangerous, we will write everything in Pascal. No, we will write things in a subset of C or C++, that where the chances of committing dangerous mistakes have been reduced. So we will use a subset of the language. We will avoid the dark corners of the language as much as possible. And language subsetting is mandated or recommended by all major safety and security industry standards. And today, the most authoritative language subset for C programming language is MISRA C. I will try now to introduce, for those of you that don't know MISRA C, give you just a quick idea of what it is. So I will present just 3 rules, okay? MISRA C is encoded in a set of rules. There is much in MISRA C beyond the rules. There is the deviation process, which is essential, but let's now just focus on the rule. So the first rule I am presenting is rule 1.1, which is very important. And as you will understand from Marcel's presentation, it has a role also in compiler qualification. It says, the program shall contain no violations of the standard C syntax and constraints and shall not exceed the implementation translation limit. Okay, so the program has really to be coded in C. Okay, And it should not go beyond what the C standard mandates, because otherwise there is no specification, no agreed upon specification. Okay, there are several reasons why we have this rule. One that is internal to MISRA. So language features that are outside the supported version of C have not been considered when developing the MISRA guidelines. So the safety guarantees provided by MISRA are not valid if you go outside the language. But there are other reasons. For example, a conforming implementation does not need to generate a diagnostic when a translation limit is exceeded. An example of translation limit. So a C compiler in order to be called the C compiler, has to guarantee that nesting of sharp if constructs is permissible until a certain depth. Okay, if you exceed this depth, then you are exceeded a translation limit. So maybe your compiler will be more generous, and it will allow you to nest conditional compilation directives more deeply than what the standard guarantees. But if it does not, the compiler can be standard without a requirement of providing you a diagnostic. Okay, and so you risk generating an executable that has surprising results. And also there are many implementations around that are technically non-conforming because they do not diagnose constant violation. Okay, so in contrast to exceeding translation limits, whenever there is a constant violation, according to the C standard, the compiler has to issue a diagnostic. And well, there are many compilers that do not this. Okay, so you will see this in a few minutes when Marcel will talk about the X tests that are meant to check whether a compiler is providing all the diagnostics that is supposed to provide. And many do not do this. And clearly, enforcing MISRA C rule 1.1 is a mitigation, because the compiler is not telling you, but the MISRA checker will tell you. This rule has been chosen because there are some, because it's easy, and because there are preconceptions. Someone might think, hey, why you are talking about comments? What may be wrong with comments? Well, there are things that may go wrong with comments. First of all, comments in C can be introduced by the double slash or by the most traditional method slash star star slash, and they combine in ways that are more complicated than one might think. And also they interact with so-called line splicing. Here is an example of line splicing. Here, the programmer wanted to emphasize that this SRC thing in the project folder is itself a folder. So that's why the programmer put a backslash at the end of the path. And however, this backslash happens to be at the end of the line. So this is line splicing. Line splicing means that critical function become part of the comment. So critical function, independently from what the programmer believes, it's not a function call. It's just part of the comment. Okay, so that's why the rule says line splicing shall not be used in double slash comment. So the MISRA checker will warn you, and whereas a compiler will not warn you about this because it's perfectly legal. See this one. Rule 13.2 has to do with unspecified behavior. So let me just go to the examples here. So one thing that is unspecified is the order in which in a function call the arguments are evaluated. So in Java, for example, the order is left to right. But in C, it's unspecified, meaning that in this example where we have a function call with two arguments, the first one may be evaluated before or after the second. So in many cases, it will not make a difference. In this case, it makes a difference because the arguments are volatile. And reading a volatile is a side effect that in general is observable from the outside of the program. So this is unspecified behavior. And if we write this line, we will not be able to say whether the side effect of TCNT1 will occur before or after the other one. So the solution to be complying to the guideline is to introduce local variables so as to force the intended order of execution. Okay, so for compiler qualification, over to Marcel.
Thank you, Roberto. You can make me presenter. Yes.
There you go.
Thank you.
You should be able to, there you go. Now I can see your screen, Marcel.
Yes, thank you.
Great.
All right,
you.
so my name is Marcel Beemster. I'm the CTO of Solids Sands. Yeah, you made Solids Sands from our supertest compiler and library validation suite for C and C++. Recently, we introduced also Supercard specifically for library qualification, but today we'll talk more about compiler qualification. So yeah, let's have a brief look at compilers. Compilers are very complicated, and this picture shows the program going into the front end of the compiler, then moving all through the compiler, all these stages of the compiler coming out as assembly on the other side. And there's a bit of a butterfly effect here, because even a small change in the input program, or even a small change in one of the optimization stages here, can cause this red line, the path of the program through the compiler, to change. And that makes it hard to find errors. And it also makes it the compiler quite sensitive to errors. Errors are not really localized in the sense that an error in one specific optimization may have an influence much later. So that's difficult with compilers. Compilers are hugely important development tools because all your application code goes through it. And they're also very big. The typical compilers are maybe in the order of 5 million lines of code. So that's quite a lot. If we use Supertest to do a qualification on a by default C++ compiler, then we find that there are quite a lot of errors. So we differentiate between compile time errors, that is when the compiler compiles a program that it should not compile because there's an error in it, or when the compiler fails to compile a correct program. Those are compile time errors. And you see for this default setting, we have 103 errors for this compiler. And we also have runtime errors. Now, the fewer runtime errors, only 4, but they are often quite specific for a compiler. So the diagnostic errors, the compiler errors, they're very often of the same kind. The runtime errors, they're often quite specific. Now, let's take a look at some of these errors. Here's a fairly harmless error. This is a piece of C++ code that should not compile. And what happens for LLVM 3.9, so it's an old version of LLVM, you will not run into that with the latest version. But when you compile this program, the compiler will simply crash, and you'll see a long crash report from the compiler. Now that is not so nice, but it's not dangerous in the sense of safety critical, because the compiler doesn't generate any code that can end up in a safety critical application. That's different with this error, and this is an error due to this test from Supertest. It starts with an X. It means it's a diagnostic test, and that means that this program contains an error. It's not conforming to the C standard, and so the compiler is expected to give a diagnostic. Now, in this case, we have here the colon, the question mark colon construct, the conditional expression construct, without a middle expression, so it's left blank. Now, this is an extension to the GCC compiler, which was taken over by LLVM, and that's one of those cases where, you have an extension that if you want to abide to the MISRA rules, you're not supposed to use, and so therefore you do expect a diagnostic for this program, but whether the compiler gives that to you or not, that depends on many things. Something that you want to avoid, and therefore this could be marked as a diagnostic failure of the compiler. Yeah, you might think, okay, why do I need to test a GCC compiler, for example? Because there's Bugzilla, it lists all the bugs. Now, this indicates the importance of what we also call the use case, how the compiler is used exactly, what version of the compiler, what optimization settings, etc. So, first of all, Bugzilla is huge. There are more than 100,000, in the order of 100, no, more than 100,000. Here we see identifiers above 100,000, and they really started at 0 issues in Bugzilla. And this is a list of open issues, and you see here it says there are 10,000 open issues. There are more, but it also says, okay, this list is too long for Bugzilla's little mind. So actually there are more than 10,000 open issues with GCC. Is that very bad? Yeah, I don't know, because it's very hard to figure out which of these issues apply to your use case in your compiler. These issues are usually linked with a specific version, but there's no guarantee that it is linked with all the versions of GCC that the error appears in. It is only linked with the version that it was found for, and sometimes someone is so nice that they also put in some other versions. Also, most of them are very specific. So here, this error, the top one, is specific to optimization level 2 and certain other settings for optimization. So it's not so easy to figure out. Actually, I would say it's impossible for you to figure out with this list what errors apply to your implementation of GCC. So another example of the importance of the use case is this runtime error that we found with Supertest. And it happens when you compile a program on Linux subsystem version 1 on a Windows machine. So it's a compiler for Linux, but it's generating code for Windows. And Windows supports that in Linux subsystem v1. But this expression over here that you expect to be true, where you have a variable, you add something small to it, then you expect the result to be at least as large as LD5. You expect it to greater or equal to be the original version. Now this fails for this particular instance for this use case, and actually this happens because the compiler thinks it's running on a 80-bit floating point machine, but Windows actually only uses 64-bit accurate floating point. And so in the Windows system, the Windows hardware is set to round to 64 bits. So the operation on this side is rounded down to 64 bits, losing a number of significant bits, while this value is loaded by the compiler into the hardware unit at the precision of 80 bits. And then you get this failure. So the compiler is actually okay. It thinks it's generating correct code for an 80-bit machine. The Windows operating system and hardware is also okay because that is specified to be 64 bits. But the integration between the two, the use case, that fails. Now, can this possibly be harmful? And then we move on to the area of safety and safety critical issues with compilers. Yeah, here's an example of safety, when safety can affect certain cars, for example. So this example is for the Nuna X. It's a solar car participating in 2019 in the World Solar Challenge in Australia, a race over 3,000 kilometers, and it was en route to win the race. And it only had 3 hours to go before the finish. And at that time, disaster struck. So they had been running 3 days already, but in the last 3 hours, this happened. The driver felt something warm at his feet. He steered the car into the side of the road. He quickly got out of it in time, so nobody was hurt here. But within a time span of a couple of minutes, less than 5 minutes, the car was reduced to absolutely nothing. Obviously, the team wanted to know what was wrong with the car, and they wanted to see what the error was. The race was, I think, in October 2019. In January 2020, 3 months later, they issued a press statement that they had not found the error. They didn't know whether this was caused by the wiring, the hardware, chips, the ECU system, the power system. They had no clue. They could not find in this rubble what was the problem. Now, in theory, it could have been a compiler error. If we have this error that I just showed you with the rounding problem, with a mismatched use case, if that would be part of this loop that takes care of battery charging, that loop might check, well, I have my battery charged now. If I level up a little bit, am I still below the maximum charge? Well, if this loop never ends, then your battery system might get overheated and perhaps cause an error. So this is one reason to make sure you want to make sure that your compiler is correct. So the goal of compiler qualification in the goal of functional safety, but also security, is to develop confidence in the use of the compiler. And Roberta already said, if you don't have that confidence, if you don't trust your compiler, which is what happens when you have much stricter requirements for the compiler, if you don't trust your compiler, that means that you have to verify the assembly code that the compiler generates. And that puts you in a very big trouble, because checking the assembly code is a huge amount of effort, and it means that you are restricted in making updates of your application code, because every time you fix an error in your application code, you have to go through the checking of the assembly code. Now, that's a huge effort, and that's the reason why you want to develop enough confidence in your compiler so that you can use it for safety critical applications. Now, that process of tool qualification, compiler qualification, is formalized in the ISO 26262 standard. It's one of a number of different functional safety standards, and this one is for the automotive industry. And the nice thing of it is that it really describes a nice process of tool qualification. And very important is that tool qualification is the responsibility of the application developer. The application developer picks their tools, and they have to make sure that their tools are sufficiently reliable to do their job. That also holds for the compiler. Now, compiler qualification might seem a daunting task to an application developer, but that's why we developed Supertest. We have done a number of different compiler qualifications with Supertest, and also our customers are using Supertest for compiler qualification. So with the right test suite like Supertest, that is quite possible to do. As I said, the automotive functional safety standard, it defines a very nice process. It really spells out, okay, this is what you have to do first, then you do that, then you do the next step. I'm not going through everything in detail here, but some important steps are here: the choice of your qualification method, and then finally the validation itself, of course, and then writing down the problems that you found in the compiler, and put that in a safety manual. So for the qualification methods, there are a number of different choices. Now, basically, the only one that is feasible is validation of the tool with a test suite, with a tool that with a test suite that can verify that the compiler generates code with the right behavior. So that's what we typically do. Supertest is a test suite that is written in such a way that you can trace back all the tests to the language specification. So it in the V model, it fits sort of at the mid-level. It's not a unit test. These are basically black box tests. Supertest test suite verify the behavior that's observed from the compiler generated code. And that is how we can check that the language implementation is correctly done by the compiler. Documentation, very important there is of course to document the whole process. This is what you need if you want to provide your documentation to an independent auditor. and they can say, okay, you properly followed the process, and here you have a stamp of approval. And part of this documentation is going to be the compiler safety manual. And that is because you need to address the errors that you have found in the compiler. We have done many compiler qualifications. We've never seen any compiler without any errors that are safety critical. So there will also always be safety critical errors, and you have to write them down in the safety manual. And the safety manual describes for the application developer what is needed to safely program with this compiler. And then you're done, your qualification process is complete. But then there is, of course, this catch, because the application developer now has the responsibility of following the safety manual. And yeah, there are a number of different ways for that. One of them is go through the application, to the safety manual, and for the application, manually check that all the requirements in the safety manual are met by the application. Now, that can be a huge effort. We recently talked to a manager and an engineer who had done compiler qualification in the past, and the manager asked the engineer, how much time is it to verify the application according to the safety manual? The engineer said it cost me 1 week. And then the manager was quite silent, because that was a huge effort and he had not expected that. It's also, if you do that, it's easy to make a mistake. If there are 10, 20 different rules that you have to follow, then an automated solution is much preferable. Now, actually, what the safety manual does is also subset the language. So like the MISRA guidelines, the safety manual says, okay, don't use this in your C code. So therefore, static analysis tools like ECLAIR from BUGSENG are eminently suitable to find these kind of further restrictions of the language. And that's why BUGSENG has introduced the application hazard scanner. The application hazard scanner can be configured to specifically verify that the additional rules that are written in the safety manual are also followed in the program. So this makes the whole process automated, and that of course makes it a lot faster to do that, and you can give that to the developers themselves. They don't have to be specialists. It's less error prone, and yeah, it's a huge saving of effort. You might think, okay, it might be a huge effort to write down all of the problems that you find in the compiler and make new checks in the hazard scanner, but actually many of the errors are diagnostic failures. Many compilers don't issue the right diagnostics, and if you have a good MISRA scanner already, then those diagnostic errors will already be in the hazard scanner, and you only need to treat the very compiler-specific issues. Now, two examples of those very specific compiler problems are this runtime error. I'm not going to complete, well, I'm going to do it. So here we have a structure for the house. It has a contact address in it, and here we initialize the house. We initialize the variable home, and we initialize the contact part by a generic contact address. And then specifically, we override the phone number field with 650. If you feed this to GCC, and as far as now, this is been part of GCC for a very, very long time, since this construct was introduced in 1999, because the language specification wasn't quite precise, and so it was incorrectly interpreted by GCC developers. And this bug is never been fixed. Oops, my screen, why is that happening? Am I still there?
Marcel, you're still presenter, so
yeah.
I'm not sure if you just close the. There you go. We can see it back now.
My presentation software crashed.
Yeah,
that's a surprise. Okay, so here we override the specific phone number field by something else. And in GCC, that is still an error, and it's not fixed to this day. So this can happen in your application as well. This is another one, and this is much more tricky. What's going on here is C++. There's again a nested class definition, or inheritance, actually, inherited class definition. And here we have a cast from the class pointer to a void pointer, and then there's a cast back to the original class pointer. Now you might think, well, this is very, very strange code. You would never write code like this. So, but if you want to make sure, yeah, you need to scan your software for that. And as you can see, it's not so trivial to find this. This is actually quite tricky. And to scan your software for such an occurrence is very hard, actually. So that is why you want to have the application hazard scanner. So I'm giving the screen back to Roberto. So maybe you can show some examples, Roberto.
Okay. Roberto, you're presenting now. Thank you, Marcel. Roberto, whenever you're ready to share.
Yes.
There it is. Okay.
Okay, it's time for a quick poll now.
Yes. Let me launch it. Okay, you should see it all now. So were you ever hit by a compiler bug?
I did, more than once.
Okay, let me just give a little bit of time. So we have a few replies already. So 25% said never, 25% said once, 25% more than once, and 25% too often for my taste. So we have a pretty generic answer here.
Okay, so
Okay,
we have
thank
all
you,
the
guys.
combinations.
Yeah.
This is undecidable.
I don't know.
Okay.
No, they're still like this, so it's definite.
Okay. Okay. So the application has a scanner. There is before in presenting the application as a scanner, I would like to make another comment about the role of language subsetting. It has to do with extensions. So the point is that the compiler qualification effort is done with respect to a specification of the language, and the language is given by the ISO standard. Okay, and the ISO standard doesn't include extensions. So this is one of the reasons why in the MISRA standard the use of extension is limited. So you have to justify the use of any extension. So the ways in which language subsetting and compiler qualification go hand in hand are three, and I will present a fourth one. The first three are enforcing standard syntax and constraints, enforcing translation limits, limiting the use of extension, and now we see the application as a scanner. So compiler qualification enables the use of C, C++. You cannot use C or C++ if you cannot count on the correctness of the compiler. And language subsetting also ensures compiler qualification is relevant, so that you are you have tested something that is relevant to your application. Your application doesn't go beyond the standard. So let's see example of the application as a scanner. So let's start from the bug that Marcel showed last. So the one affecting C++, a certain version of GCC, when you cast a void pointer back to a pointer of class type, but only when the class type inherits from another class. So the presence or absence of the bug in the GNU version of the compiler does not follow a trivial pattern. So 7.4 has the bug, 7.5 was fixed, 8.1, 2, and 3 have the bug, and it was fixed, hopefully, once and for all in 9.1 and later version. But the point is that GCC is used as the basis for many GCC derivatives. So is your compiler affected or not? And if it is affected, is your application affected or not? So this is not easy to detect by hand. So let me show you an example of the application ASA scanner, which has been instantiated over this GCC bug 89698, which is the one that we were talking about in a second ago. So we have analyzed several open source projects. We found 6 occurrences of this potential issue in a project which is quite large. So it's called LIX. It's what you see is what you get editor for LaTeX. You see that there are thousands of source files. So I am presenting just the results here. So this application is affected in 6 different places. You see here, the AHS is short for Application ASA Scanner, GCC, and the bug identification number. And we have a report saying that we have a static cast from void pointer to a class type that blah, blah, blah. Okay, as you see, the issue is identified precisely here. So let me switch to the other example. I have to find my slides first. Here they are. Okay, this is the other bug Marcel explained, the bug whereby when you override, your intention is to override just the phone number and leaving the fax number alone, unchanged. In reality, what will happen due to this bug is that you are overriding the phone number, which is expected, and you are also zeroing the fax number, which is not expected. So let me show you this using the application ASA scanner itself. What is it? It's an incarnation of ECLAIR. Okay, so it's ECLAIR. Here you see that we enabled the application ASA scanner, which has been instantiated over these 2 defects that we have illustrated here. We can run the analysis here. ECLAIR analyzes the program during the build. So you see that there is the build analysis phase, and then the reports have been constructed, and now we can inspect the reports that have been generated. Here it is. Okay, you see that we have found 3 issues. Okay, so we have found 2 issues concerning the bug having to do with overriding fields of a structure that were meant not to be overridden, and we have found 1 about the C++ code where a cast to void pointer causes the issue. So let me look at these 2 violations of GCC. You see the message is code is vulnerable to GCC bug 63944. Okay, here is exactly the example shown by Marcel. And so you see that the message is very precise. It's saying, hey, here we have a problem. And in fact, this is the overriding assignments, and this is what is being overridden. Okay, so it's very precise. Okay, here is what the problem is. Here is the overriding assignment, and this is what is being overridden. Okay, we have also another issue that this time is taken exactly from the C18 standard. So this is example 12 in C18, which explain what should happen. And okay, here is where the problem is. Here is the assignment that is overriding. And what are we overriding? We are overriding this. Okay, so what is overridden in the defective compiler versions, which is all version of TCC actually. This K field is overridden. It should remain 42 if the code was compiled corrected, and in fact it is overridden. Okay, and then let me go back. Let us have a look to the other one, but we have already seen this. It's a simpler, this is taken from Marcel's slide. It's the non-compliant cast from void pointer to B pointer, okay? And the problem here is that B is a class that inherits from another class. So, and in this case, we have that code is vulnerable to GCC bug 89698. Okay, so this is for the presentation. Now I will, sooner or later, I will find the slides. I found them. Conclusion. So there are concrete advantages of MISRA compliance and compiler qualification besides checking the box. They reduce time to market in different ways. For example, MISRA compliance allows very often to obtain the final product with much less overhead due to reworking and retesting, because you are preventing a lot of defects that otherwise you would discover later, and you will have to redo a lot of work, maybe also testing work. And concerning compiler qualification, one of the advantages is that you can decouple application development from compiler testing. It's a mistake to do compiler qualification only at the end. You want to know in advance the problems that you have with the compiler. And so doing MISRA compliance and compiler qualification allows you to sleep better, because a significant portion of you work in safety critical projects. So this is something that you have to take into account. It is a piece of news of the recent days that the NHTSA, so the US agencies that have to do with the safety, traffic safety, so automotive safety, has asked Tesla to provide a lot of details about their cars, including the software, including the kind of testing, the kind of measures that they take to mitigate potential issues. So my belief is that Tesla will have to provide details about the techniques they use internally to make sure that the software is safe. The application ASA scanner enters into this picture, giving another important way where static analysis and compiler qualification go hand in hand. Application ASA scanner solves the long-standing issue of what to do once you discover the compiler defect. As Marcel said before, there are a significant number of people who spend their time to match the compiler safety manual resulting from a tool qualification exercise, to match it manually to the application source. And this is clearly very, very inefficient, very error prone, something that you have to redo every time you make an update. And so it's something that ideally should be automatized, and the application ASA scanner has been conceived precisely for that. Okay, so if there are questions, we can try to answer.
Thank you, Roberto. We have several questions for Marcel, if I can start from him. So how long does it take to qualify a compiler and generate a qualification report?
Let me unmute. Yes. Yeah, I would say it depends. I think that the shortest time frame would be in the order of 2 weeks. There's a couple of things to consider. First is the startup time. You need to configure the test suite for the specific compiler and also the hardware target. If you want to take the hardware target into the use case and validate on that, that may take some time to get the hardware, the compiler integration and the hardware target configuration with the test suite running. Often that is very easy, but that sometimes it takes a couple of days to figure out all the information that you need. Then the actual test run, maybe a bit slow. If you're running on target hardware and it takes a lot of time to run one program because you have to download the program into the target hardware, then the test run itself may take quite a number of days to do. So that takes time. And then the analysis phase, how are you going then to deal with the bugs? What kinds of bugs are there? When we do this for a customer, we typically talk to the customer, discuss, we found these kind of bugs. We know if you turn off this specific optimization in the compiler, then this bug disappears. Do you want to change your use case to make this bug disappear? Or do you want to have this bug in your safety manual? So that is a discussion we have with the customer, and that also determines a bit of the time it takes. So I would say the fastest time is maybe 2 weeks, and if it goes, maybe typically it's about 4 to 6 weeks, the whole time frame.
Okay, good. Thank you, Marcel. It seems that GCC has a lot of issues, and that raises the question, is it possible to qualify open source compilers? The process and the risks are different from the qualification of a proprietary compiler.
From the process perspective, actually not. Because I've shown you the 4 different qualification methods. If you choose the verification of the compiler, you're independent of where the compiler comes from. The fact that GCC has a lot of documented bugs does not mean that other compilers do not have those bugs, even if they may not be so visibly documented, because of course GCC compiler is a very open and very visible project. In fact, we have done a number of qualifications of GCC and other open source compilers, also for different functional safety standards, also industrial standard, that's used also for robotics, and the rail standard for railway. The functional safety standard, they don't ask, is this tool open source or not? They just provide the process, and if you follow that process, you can do the qualification.
Okay. You quickly skipped over the confidence from use argument for qualification in favor of using super test. Why is confidence from use not possible?
Confidence of use is one of the 4 methods of compiler qualification, and it has to do a little bit with the first picture that I showed of the complexity of the compiler pipeline. If you have a piece of software that's very modular and very distributed, and one part does not affect another part, then you can rely on confidence from use even when you go to a new version of that piece of software, because there's only a few components are modified. But with a compiler, because of the pipeline structure, if you go to a new version of the compiler, it basically means you have to redo the qualification, because this is a new compiler. Even a small change in one component can affect everything that happens after it and introduce an error. Maybe not in the component that was changed, but it may expose an error down the pipeline. So confidence from use is only usable if you use the same compiler for a long time, no updates of versions, and also probably for a similar use case, so the same options, and also the same type of application. If you change your application completely, try to compile a different application, that means that the compiler path is going to be changed completely. It's not the same use of the compiler. So that is an argument that's just hard to make for compilers. People don't use the compilers that are 5 years old for a long time, unless it is in one project and it stays within that project. So in general, yeah, compilers, there are the different versions are too different to use that argument.
Thank you, Marcel. We got a couple of questions about how to purchase the application as a scanner. Of course, it's a part of Solids Sands Compiler Qualification Service. So you can either write to both our addresses, the one that you see on the screen, and we will get in touch and we can, of course, schedule a call, given that, of course, it's a customized service. It all depends on your specific use case. So moving on with next question. I think this one is for Roberto. How complicated is to create a checker for a new compiler bug?
Well, it depends. So usually there is a preliminary analysis phase that is conducted by Solids Sands experts. So a bug has to be somehow circumscribed to a series of situations causing the bugs. Sometimes there are official sources, for example, Bugzilla, where part of the work has been done by the compiler suppliers, and in other cases, this will require analysis from on the part of Solids Sands and BUGSENG personnel, so that the mitigation can be defined. And then typically the effort of producing a checker for a compiler bug can involve I don't know, depends, for the very easy 3 to 5 days of work of a suitably skilled engineer.
Okay.
I mean, this includes everything. Of course, you cannot just implement something and then release it in the wild. The checker has to be designed, implemented, and of course, it has to be tested and validated.
Of course. Okay, for more information, of course, we will follow up with a post-webinar mailing. So you can refer to the articles and links that we posted in the Q&A section, but of course, we will combine them all in the post-webinar mailing. So don't be afraid of losing anything. You'll get it afterwards this afternoon or later tomorrow. Okay, so if there are no more questions, I think we can conclude. It's almost 10 past midday. So again, thank you, Roberto, and of course a special thanks to Marcel and to all of you for attending. Clearly, if more questions come to mind later, you can always write to info@bugseng.com and to info@solidsands.nl. Both our teams are available in case you'd like to schedule a call and discuss your specific requirements in terms of compiler qualification and, of course, MISRA compliance. If you'd like to refer back to this webinar or share it with your colleagues, the recording will soon be available on BUGSENG and Solids Sands YouTube channels. You can find the links in the Q&A section and afterwards in the post-webinar mailing. Make sure you subscribe and turn on the little notification bells to get notified when we upload something new. I hope to see you all next time on September 29th for next webinar, which will be a guided tour of the new feature in ECLAIR. This one is particularly useful to current users to freshen up their knowledge of the tool, and as well, of course, as to future users to get a good overview of how ECLAIR works. Right, so this is it from us today. So until next time, have a nice day, everybody. Bye, Marcel. Bye, Roberto. Thank you again.
Bye-bye.
Thank you all. Bye-bye.
Bye. Thank you.